Hello everyone. To all the venerated members of the audience, I extend a warm welcome to my presentation. I am honored to be presenting before you. The title of my presentation is Modernizing Medicine Through a Proof of Concept that studies the intersection of robotic exoskeletons, computational capacities, and dementia care. Now, what I want to highlight here is what a proof of concept is. A proof of concept studies the feasibility of a technology, of a proposed technology. With this, let me begin with the presentation. I am Ritvik Raj Saxena, one of the authors of the paper. Let's begin the presentation by diving into the overview. We will first talk about dementia. What dementia is. Dementia is a degenerative disorder of the brain. It is primarily associated with old age, but it can also occur in young people. As we know it, we primarily associate dementia with memory loss and cognitive decline. Yes, cognitive decline is a primary feature of dementia, but dementia also features mobility problems. The mobility problems especially occur in later stages of dementia. While traditional and current rehabilitative methods have shown promise, they are not a complete solution for care of dementia patients. Robotic exoskeletons have demonstrated as being beneficial in many other diseases that affect movement. For example, paralysis due to stroke and other neurodegenerative disorders, musculoskeletal disorders that affect movement, for example, Guillain-Barré syndrome, Parkinsonism, and so on. Exoskeletons primarily target mobility issues. We believe that exoskeletons incorporated with artificial intelligence systems could help dementia patients by improving their movement, independence, and quality of life. Artificial intelligence can, to some extent, help with cognitive recession, while exoskeletons themselves can help with mobility issues, thereby improving quality of life of dementia patients. There are challenges that are associated with this idea. When a new technology is being talked about, there are always challenges associated with it. In most cases, it is user acceptance. And then a new technology is always costly. So there are cost challenges associated with a new technology, and then we have long-term effectiveness. Robotic exoskeletons could prove to be a new way to improve mobility and quality of life for dementia patients. A technology has to be something that is a far-reaching improvement over existing technologies. A new technology should be something that is a large step, a large amount of improvement over the existing technology. Only then it can be long-term effective. Now we'll talk about dementia in detail. Dementia is an intricate medical condition which causes cognitive decline and physical decline. Cognitive decline is of many kinds. It has many aspects associated with it. For example, memory loss, language inconveniences, mood changes, and behavioral problems. There are reasoning deficits, difficulty with daily cognitive tasks, and also other aspects that are associated with it. Physical decline involves motor skill impairments, difficulty with balance, difficulty with physical tasks, and disorientation. Now, the most common form of dementia is Alzheimer's disease. It usually occurs in 60 to 70% of cases with dementia. Other forms of dementia are Lewy body dementia, frontotemporal dementia, vascular dementia, and mixed dementia. We'll talk about this in detail in upcoming slides. Based on the data from the 2010 World Alzheimer Report, the number of people with dementia is projected to rise much faster than the overall global population, with estimates indicating a jump from 35.6 million in 2010 to 115.4 million by 2050. With dementia growing disproportionately to the global population, a future is foreseen where innovative solutions for dementia are an imperative demand. Now, how is dementia diagnosed? Diagnosis is done using medical history, physical exams, cognitive testing, and brain imaging. Brain imaging can be of various kinds: MRI, CT, and PET scans. MRI is magnetic resonance imaging, CT is CAT scan, and PET is positron emission tomography. CAT scans imply computer-aided tomography. Now, dementia has no cure. Most diseases of brain have no cure. If we come across a disease that has no cure, there is a high probability that it is a brain-associated disease. The treatments of dementia aim to manage symptoms. This is called palliative care. They are only focused on longevity, improving the longevity, whatever longevity remains. Early diagnosis is crucial for better treatment. Research explores new treatments that utilize technology like robotic exoskeletons and artificial intelligence. That's where modern research is working in the case of dementia. This slide is just a continuation of the previous slide, and it discusses the same statistics in greater detail, those that we discussed in the previous slide. We can see that the number of people with dementia was 35.6 million in 2010. In 2024, it is estimated that 59.9 million people will be affected by dementia. By 2030, 65.7 million people will be affected by dementia. And by 2050, 115.4 million people will be affected by dementia. That's what it is projected to be. This is much faster than the global population growth. The rate is much bigger. That's what it is being emphasized here. This slide is also a continuation of the slide on dementia. Alzheimer's disease, Lewy body dementia, frontotemporal dementia. These three dementias are collectively termed Alzheimer's type dementia. Alzheimer's type dementias occur because of malfunction in proteins. Among these, Alzheimer's disease is the most common form. It is caused by malfunction of certain transporter proteins in the blood-brain barrier. The blood-brain barrier is there to wash away or cleanse unneeded or harmful chemicals that are generated in the brain, usually as waste. The malfunction of those transporter proteins hinders the flow of glucose in the brain, hampering brain nourishment. blood-brain barrier also ensures that no other source of energy reaches the brain except glucose. Once the blood-brain barrier malfunctions, brain stops getting glucose or gets less glucose than it needs, thereby facing damage and even death. Dementia's main feature is that the brain starts constricting. The beta amyloid and tau proteins are waste proteins, and when they are not cleansed because of the malfunction of the blood-brain barrier, they settle at various locations in the brain, disabling the neurons. In Lewy body dementia, the insoluble form of otherwise soluble alpha-synuclein, an unfolded protein, aggregates as inclusions termed Lewy bodies. They are also found in Parkinson's disease and other synucleinopathies, including the type of dementia we term Lewy body dementia. Frontotemporal dementia is the least common Alzheimer's type dementia. It is caused by deposition of tau and TDP43 proteins in frontal and temporal lobes, and this results in a rare type of dementia called frontotemporal dementia, which is also called Pick's disease. The distinctive feature of this disease is called knife blade atrophy. The brain is filled with spaces called sulci. The singular of sulci is sulcus. A sulcus is a very narrow gap. When it starts broadening, when the brain matter starts shrinking, we say that the brain is suffering damage. Now, when these sulci broaden to look like blades of a knife, that's when we call it knife blade atrophy. This is a severe form of atrophy, and the brain matter reduces exponentially. Vascular dementia is set apart from Alzheimer's type dementias in that the flow of blood to the brain reduces in vascular dementia. Blood carries important nutrients like we saw glucose as well as oxygen to the brain. When the flow of blood to the brain reduces, the access of brain to these important compounds like oxygen and glucose reduces, leading to damage to the brain, which leads to vascular dementia. Vascular blockages, vascular damage, embolisms, clots, aneurysms, strokes, cardiac insufficiency, they may all cause vascular dementia. Vascular dementia results in global cortical atrophy. Typically, the brain has an area called cortex, and this cortex is severely atrophied in vascular dementia. In frontotemporal dementia, the frontal and temporal lobes cortex was atrophied. In vascular dementia, all the cortex is atrophied. White matter lesions, lacunes, and strategic infarcts are also seen in vascular dementia, and they are unique to this kind of dementia. Therefore, vascular dementia is also termed multi-infarct dementia. Mixed dementia features one of Alzheimer's type dementias as well as vascular dementia. It can feature one or more types of Alzheimer's type dementia and vascular dementia. Now we come to progression of dementia. Before dementia starts, we can start seeing symptoms of dementia if we observe carefully. Dementia often goes unnoticed and undiagnosed before it starts and even in its early stage. That's why we say subtle symptoms. Subtle symptoms emerge and go unnoticed by others in the early stage. Memory lapses affect tasks like recalling recent events or finding misplaced items. Personality changes, behavioral changes, such as increased irritability and anxiety, become apparent. Individuals may still function independently, but struggle with complex tasks like managing finances and expressing thoughts. Managing finances requires analytical reasoning, while expressing thoughts require emotional intelligence. So both logical as well as emotional aspects are affected in dementia. fMRI implies functional MRI. It is a type of MRI. fMRI scans may show reduced activity in the hippocampus, crucial for memory formation, which may also present before dementia onset. Hippocampus is an important part of the brain and is associated with memory. It is a part of the limbic system within the brain and it is associated with basal ganglia. The early stage typically lasts around 2 years. Now the middle stage. Middle stage is where the symptoms of dementia are actually visible. Cognitive symptoms worsen, making daily tasks like dressing, eating, and bathing challenging, requiring caregiver assistance. Confusion and forgetfulness escalate, with individuals repeating themselves and forgetting names of loved ones. Behavioral changes, including agitation and paranoia, become more frequent. PET scans reveal decreased glucose metabolism in memory and reasoning brain regions, while MRI shows significant decline in gray matter. This stage, lasting between 2 and 4 years, sees a pronounced decline in cognitive and physical disability. This is probably the longest stage. Now the late stage. In the late stage, the person is completely on external aid. They cannot survive on their own. Full-time assistance and supervision is needed. Communication is severely affected. There is an inability to recognize faces. Physical abilities decline, leading to difficulties with walking, swallowing, and other daily tasks. Life expectancy reduces and susceptibility to infections increases. The brain matter decreases to such an extent that it loses control on the immune system. Therefore, when a microbe or a pathogen presents itself, the brain cannot activate the immune system. MRI scans show significant brain tissue shrinkage. And as we talked about sulci, they are broadened here. End-of-life dementia care is required, which usually culminates in the death of the patient. This stage is the shortest of the three and typically lasts between 1 to 2 years. Now we have seen what dementia is, what dementia involves, what it entails. Having seen that, we come to exoskeletons. What are exoskeletons or robotic exoskeletons? They are external devices which improve bodily function, physical function, voluntary function, musculoskeletal function. They are all synonymous terms. They assist, restore, and/or strengthen physical movement. While bodily function, the term bodily function may refer to all kinds of bodily function. Physical function refers to voluntary function. Types of exoskeletons. There are many benchmarks, many criteria on which exoskeletons can be differentiated. The first type of exoskeletons that we will study is rehabilitative or restorative exoskeletons, which facilitate function after injury or disease. They are made for people who have suffered from some injury or disease and have reduced mobility compared to normal people. Assistance or industrial exoskeletons augment the normal capabilities of normal people who have normal mobility for work tasks, specifically military. In certain industry, lifting of heavy objects may be required. These objects may be too heavy to lift for even a healthy human. For this purpose, an exoskeleton may be used. That's what we term as assistance or industrial exoskeleton. On the basis of actuation mechanism, exoskeletons may be classified as active exoskeletons, passive exoskeletons, pseudo-passive exoskeletons, or hybrid exoskeletons. Active exoskeletons are powered by external energy. All their functions are powered by external power. This power may be electric, pneumatic, or hydraulic. Electric is self-explanatory. Pneumatic implies air, and hydraulic implies using water to generate power. Passive exoskeletons use the wearer's own muscle power to trigger springs or gas struts, and they aim to reduce fatigue. For example, some muscles of the body which have more capacity to work, like biceps, they can be used to support the function of other muscles that have less capacity. For example, triceps or deltoid. Pseudo-passive exoskeletons use battery for sensors, but passive mechanisms for other purposes. Hybrid exoskeletons combine functional electrical stimulation or FES with powered actuation or passive actuation. Having observed the overview of what exoskeletons are, we can now shift to the history of exoskeletons and the early innovations in this area. The first patents for exoskeleton-like devices was awarded to a Russian person called Nicholas Yag in the late 19th century. The three leftmost figures, these three figures, they show Nicholas Yag's patents. They were passive exoskeletons and they used springs to improve movement for activities like walking, running, and jumping. One of the first active exoskeletons, this right here, was the Hardiman one, developed in 1960s by General Electric. This exoskeleton was powered by electricity and hydraulics and was aimed to enhance the strength and endurance of military personnel. Continuing from the slide which showed the overview of exoskeletons, we see that exoskeletons can be classified on other benchmarks also. For example, structure. When classified on the basis of structure, there are two basic kinds of exoskeletons. Rigid exoskeletons, which are solid. They are powerful but bulky and they limit movement. There are wearable exoskeletons, which are more modern exoskeletons. They are also called soft exosuits, and they are flexible, comfortable for long-term wear, and they are better for dementia patients. Wearable exoskeletons use smaller electronic components, while rigid exoskeletons can use larger electronic and electrical components. Now, according to body area supported, there are three kinds of exoskeletons: lower limb exoskeletons, upper limb exoskeletons, and full body exoskeletons. Lower limb exoskeletons, they assist with walking, standing, and climbing stairs. They basically target legs and hips. The upper limb exoskeletons fundamentally target the arms, the upper body, while the full body exoskeletons target the complete body. They support legs, trunk, as well as arms, and they are usually used for patients who suffer from extensive weakness. We now come to the workings of the robotic exoskeletons. The components of robotic exoskeletons include a lightweight adjustable frame, motors, which may include DC motors, brushless DC motors, servo motors. They are for movement purposes. There are sensors, position sensors, force sensors, and IMUs. They collect user data. There are actuators, linear actuators, rotary actuators for applying force or torque, or both. There is a control unit, which is the brain of the exoskeleton, which processes and coordinates. It processes the data collected by the sensors. There's human-machine interface for user interaction. Now the function. The sensors gather user data, movement, muscle activity. The control unit processes the data and coordinates the motors based on the processing of that data. The actuators provide movement based on control unit signals. Human-machine interface facilitates communication and feedback. The control unit processes the data collected by sensors and using the output of that processing, it can transform or modify the working of the motors and the actuators. The control unit is a part of the computational aspect of the sensors. Adaptability. Exoskeleton adjusts to user needs and environment. This optimizes function, safety, and user comfort. That's what we just talked about when we said that control unit processes data and uses it to optimize the motors and the actuators. In one of the previous slides, we saw the history of exoskeletons and some of the few exoskeletons which were patented in their inception stages. We now see some exoskeletons which are being used in the current era. These are ExoNR exoskeleton and the Reebok exoskeleton. ExoNR exoskeleton is designed for gait rehabilitation and correction of gait issues. It provides upper body support and powered leg movement. Therefore, it is a full body exoskeleton. Reebok exoskeleton is designed for individuals with spinal cord injury. It uses motors, sensors, and advanced controls. It enables walking and it rectifies gait. This shows the ExoNR device. ExoNR is being used here for gait rehabilitation. This figure shows bilateral crutches as well as the Reebok exoskeleton device that is being used in conjunction with Reebok exoskeleton. Coming to the applications of computation and artificial intelligence in dementia care. The first is early detection and diagnosis, the first application. We can analyze extensive data sets comprising medical records, imaging scans, genetic information using machine learning models. These models can discern patterns and biomarkers indicative of dementia risk. This aids in early detection and diagnosis of dementia. Artificial intelligence can be used to predict dementia onset and progression by analyzing individual risk factors, informing individuals, and recommending preventive measures. All this data, medical records, imaging scans, genetic information, and individual risk factor information has to be input to the model, artificial intelligence model, for the model to process it and give its results. Now, machine learning models can learn from patient feedback and adjust settings and optimize comfort and exoskeleton performance for dementia patients. This is where we study the predictive analytics application of computation and artificial intelligence in dementia. AI systems can help readjust exoskeleton device settings based on patient feedback. AI can analyze sensor data to detect changes in gait or posture and allow for early intervention. That's where our control unit becomes paramount. Now, monitoring and remote care. Wearable devices with artificial intelligence can monitor vital signs, activity levels, and sleep patterns of dementia patients, which in turn can alert caregivers to changes in health status and enable remote care management. Therefore, artificial intelligence can be used to monitor as well as enable remote care. For example, in case caregiver is at their home taking rest, taking a break, and there's a sudden warning that has been generated which the dementia patient themselves don't know, but their exoskeleton detect using AI. This information can be sent to the caregiver directly and set up an alarm or something like that, alerting them. The exoskeleton is therefore automatically connected to some device, mobile device, cell phone that the caregiver has. Now, we come to cognitive assessment and rehabilitation application of computation and artificial intelligence in dementia. AI-powered cognitive assessment tools can monitor cognitive function remotely. VR and gamified training programs can improve cognitive function through solving puzzles and quizzes. Chatbots and virtual assistants can help in socializing, thereby slowing brain decay and helping with cognitive rehabilitation in dementia patients. Now, assistive technologies. Artificial intelligence driven assistive technologies can help dementia patients with daily tasks. These technologies can provide medication reminders, they can assist with navigation, and they can promote social engagement, which we also talked about in the previous point. Social engagement is very necessary for dementia patients. It helps them improve their cognitive function. Solving puzzles and playing games like chess, doing quizzes, all these serve the same function, that is, improvement of cognitive function. This is very important for dementia patients. Cognitive decline, the faster it is, the faster a dementia patient will end up in their late stage. To slow cognitive decline means to enhance longevity of a dementia patient. Now, drug discovery and treatment optimization. Artificial intelligence algorithms can analyze biological data to identify potential drug targets and identify areas of treatment. AI-based decision support systems can optimize medication for dementia patients. Now, caregiver support. AI systems like chatbots and search engines can provide support to caregivers, like giving self-care tips to them, while also connecting caregivers to bigger networks of other caregivers and community resources. Now, having studied what exoskeletons are and their importance in dementia, possible importance in dementia, and also having studied how artificial intelligence can help people with dementia, we now delve into the role of intelligent exoskeletons in dementia care. We combine artificial intelligence and exoskeletons for the aid of people with dementia. The applications are multitudinous, from cognitive stimulation and rehabilitation, social interaction and engagement, to cognitive assistance and monitoring, as well as to caregiver support. The incorporation of cognitive training programs, adaptation to individual cognitive abilities, opportunities for stimulation and rehabilitation, virtual reality environments, and gamified tasks. Social interaction, group exercise sessions, socialization and peer support, enhanced communication with caregivers and family, interactive features, voice prompts, gesture recognition. So what we are doing here is we are using the exoskeleton as a mobile connection device, which can help a person with dementia connect with other people who also have dementia remotely, as well as to family members and caregivers who are not present with them physically. Health monitoring and feedback. The exoskeleton, equipped with artificial intelligence, can monitor physical activity and gait. They can provide real-time feedback to caregivers and professionals, also through mobile connection, remote connection. They can help in early detection of mobility changes, and they can also track disease progression. Mobility enhancement. Exoskeletons can help with movement assistance for mobility, prevention of muscle weakness, balance detection for fall and risk reduction, and support and stability during walking. Now, rehabilitation and physical therapy. They can help with support and physical rehabilitation, guidance in strength, balance, and motion exercises, aid in motor relearning and gait training. Rehabilitation is primarily associated with stroke, which causes vascular dementia. Motor relearning is also a term that is associated with stroke. A stroke can impair a person's motor area in the brain completely or partially, causing them to lose their movement, capability of voluntary movement. To relearn that motor capability, exoskeletons can come in handy, while also helping with physical therapy. Exoskeletons can also be utilized for day-to-day caregiver support. They can help support transfers and movement of people with dementia. Sometimes these people may want to go to walks or to get fresh air. They might also need to go to hospitals or to other places. Exoskeletons can help with assistance in activities of daily living, which we call ADL. They aid in upper body movements for independence, and they can help with assistance in self-care tasks like bathing, cleaning, defecating, urinating, all these tasks. Activities of daily living include eating, combing hair, wearing a dress, and so on. As to cognitive assistance and monitoring, exoskeletons can be used for navigation assistance, medication reminders, and detection of vital activity. We have examined what the application of intelligent exoskeletons in dementia can be. Now we see human-machine interaction consideration in exoskeletons for dementia care. Human-machine interaction is a concept that is applied whenever humans and machines come together, and humans and machine interact with each other. This concept can be applied even to a person who is like me, giving a presentation using a laptop or a computer. Computer is a machine, and I as a human am interacting with that machine. This is called human-machine interaction. In case of exoskeletons, human-machine interaction considerations include caregivers needing training to manage patients using AI-powered exoskeletons. As we discussed previously, new technologies need to be accepted by their users, by all the people associated with it, including caregivers, the family members. The caregivers must be trained to utilize the exoskeletons to their own and to the benefit of the dementia patient, so that the exoskeleton can be utilized to the best of its purpose for the rehabilitation and other purposes that it serves. Patients and families need clear explanations about exoskeletons. The technicality involved in using exoskeletons can dissuade caregivers from working with patients who use exoskeletons. Training may be a tedious process, therefore giving higher remuneration to caregivers who are trained or who are undergoing training in assisting dementia patients who use exoskeletons can improve the acceptance of such technologies, especially among caregivers. User comfort and perceived benefits are crucial for patient acceptance. Trust between caregivers and patients is also essential to facilitate adoption of such a technology. Design modifications can help avoid misinterpretations by patients. Clear, patient-friendly, verbal and visible cues can help the patients differentiate exoskeletons from other objects. For example, LED lights. Exoskeletons must not be used as tools of physical support. The exoskeleton can have voice, artificial intelligence voice, speech processing capabilities, as well as it can speak to the dementia patient as well as to the caregivers, and this can serve as a visible cue or a verbal cue. If, for example, a dementia patient starts using an exoskeleton as a crutch, the exoskeleton the sensors in the exoskeleton will be informed, and the exoskeleton voice will warn the dementia patient to not use the exoskeleton in that way. Now, healthcare providers should be receptive to patient feedback regards to the exoskeleton. Ongoing monitoring and evaluation of patient feedback is necessary to avoid agitation and distress among patients. Human-centered care and tailoring user-centric design principles can help improve user acceptance and adherence. Now we come to the challenges associated with wearable robotics in dementia care. The first challenge is that of comfort. The current design may not be ergonomic enough for long-term wear. The second challenge is that of cost. Every new technology comes with a challenge of cost. The financial limitations can prevent many patients from accessing this technology. Therefore, this technology must be made accessible to patients who have limited financial means, especially to the patients who have limited financial means. Privacy. Collecting health data raises concerns about data security and patient autonomy. So the family and the caregivers need to be involved here, who give consent for collecting data about the patient and using it. Validation. More research is needed to confirm effectiveness and safety in of exoskeletons, especially intelligent exoskeletons, in everyday use. As we said, it is a proof of concept. We are only studying its feasibility as a potential technology of future. Collaboration. Experts from various fields need to work together. We need to bring them together. That's another challenge. So that research can be carried out, feasibility studies can be carried out, and the specific patient needs can be studied, and the interventions can be tailored to those needs. That's why we use the word human-centric and personalized in the previous slide. Now we conclude the presentation. The rising number of dementia cases pose challenges for patients, caregivers, and healthcare systems. Dementia, especially late-stage dementia, can significantly limit mobility and independence of a dementia patient. Robotic exoskeletons can potentially offer a new approach to improve mobility as well as the quality of life for mid to late-stage dementia patients. These devices require careful planning for successful integration into care settings. Challenges to their integration include sensor design, user interaction, and long-term effectiveness. The sensor design must be such that it caters to the comfort of the user. Also, it must be designed in such a way that it collects only the data that has been consented by the family to be given to the caregiver or to the healthcare professional who manages the patient. For example, some sensor of an exoskeleton might use functional electrical stimulation. When the electrodes of a functional electrical stimulation device are invasive in nature, they may cause discomfort. Therefore, sensor design must be in such a way that these electrodes are not invasive in nature. Now, robotic exoskeletons with AI can prove to be a breakthrough for dementia care. Combining exoskeletons with artificial intelligence has the potential to improve life expectancy and care. This technology can empower patients and ease burdens on caregivers and healthcare systems. Inclusive design and user feedback are crucial for user acceptance of AI-driven exoskeletons in dementia care. Inclusive design implies including racial and biological dissimilarities in designing exoskeletons. As an example, gender inclusive design of an exoskeleton might take into account the increased body fat percentage of a woman, the wider hip to body ratio. Hip to body ratio is greater for a woman compared to a man. And incorporating such considerations into the design of an exoskeleton makes it an inclusive exoskeleton, makes it an inclusive design. More research and funding are needed to overcome limitation and ensure effectiveness. And by addressing all these challenges, we can improve the quality of life for dementia patients. Thank you so much for attending my presentation. I hope you liked it.